This presentation was first delivered at the Ada UK Conference 2013 in Birmingham. AdaCore has announced an ARM compiler targeting ARM Cortex CPUs, and that means that safety critical ARM code can now be written in Ada or a mix of Ada and C. The presentation will show how VectorCAST can be used to test ARM Ada code. Looking at software development and testing represented in a V model, we shall be looking at unit testing, capturing code coverage from system or functional testing, and then using our unit test cases over the life cycle of the application, as illustrated up the right hand side of the model. And in the interests of brevity, we will not be considering the possible integrations between the test tool and tools supporting design and development, as illustrated up the left-hand side. The purpose of unit testing is to verify the correctness of the implementation of algorithms and logic. So our simplest unit test case is one call to a function with controlled inputs and a mechanism to collect the outputs and verify that they're correct. Moving on, we might make multiple calls to our function under test, and that might model the passage of time. We might make a sequence of calls to a sequence of functions, and that might model or test the behavior of a finite state machine. In these cases, perhaps dependent functions have been stubbed out to focus our testing effort just on the function under test. In an integration test, dependent functions are not stubbed, and that allows us to test the flow of control as functions call each other. In all cases, we have a strong concern for the level of automation that can be achieved in our testing. Looking at the source files up the left-hand side, then the red files are the unit or the units, the packages that we want to test. So we select one or more of those, and the white rectangles are the functions or the procedures or the methods that we're going to write test cases for. The dark blue files are functions or packages that we exclude from our unit test environment, so that we will require at a minimal level stubs to satisfy the linker for called but missing functions. And we want our test tool to write those for us automatically. Our code under test might want to call real third-party object code. That could be the BSP, it could be the RTOS, it could be some third-party library. And in order to make an executable application, we will need a test driver that will provide the main, that will provide the test case input data, and that will collect and make available the test case output data items for verification. So we provide the red code. The grey code is object or library code that we provide. And the test tool will automatically write for us the green code and the dark blue code. And that result will make an executable, which is a native executable for the test tool. So that might be an x86 Windows or Linux application. But that won't test the ARM Cortex code that we're going to put in the finished product and ship to our customer. So at the very least, we certainly must use the ARM compiler, and we might run our test cases on the simulator. It might be a good place to start. It might make for easier debugging. It might make for faster test case execution. But our simulator might have some kind of defect in it, or the simulator might be correct in some way that the actual target has some kind of defect. So it's possible to execute all our test cases on the simulator and not expose problems. When we run on the simulator or the target, then we will need some method of downloading the executable into the execution environment, controlling the execution, and collecting the results. And we will need some kind of support or extension in building our test environment that is able to parse and support any language extensions that have been added to the compiler to support CPU-specific features. For example, keywords such as __ interrupt, or types such as 40-bit integers. So our unit test schematic for downloading onto the target, executing and bringing back the results might look something like this. In the example we will look at in the following part of the presentation, then the GDB client will connect to a GDB server, which will connect in turn to the JTAG controller, which will connect to the board. Functional or system testing is a completely separate branch of testing, quite often, separate from unit testing. So the idea here is that the completed executable is loaded down onto the target, and the flow of execution is stimulated through the real inputs that the target has, some kind of sensors or switches, and the test cases the code is exercised to conform to the test cases, and the outputs from the system are observed. So whether they are voltages appearing somewhere, whether they are actuators that are being operated. And we want some kind of measure of the completeness of our system testing. Where did the program counter go? And more importantly, where did the program counter not go? And we find that in typical system tests, edge conditions, error conditions, boundary conditions are not executed. So two strategies for building up sets of test cases. If we start with method 1 with unit testing, we will get some coverage. We combine that with further coverage from integration testing, and yet further coverage again from functional system testing, and most probably we will have achieved much more than 100% coverage. We will have a lot of duplication. Method 2 supposes that our application is largely complete before we start testing, and in that case we can collect our functional testing coverage and combine that with only enough testing at the unit test level to achieve 100%. So that process might be quicker and therefore cheaper. Once we've built up a large repertoire of unit test cases, then we have a possible scalability problem, managing those over the life cycle of the application. Let's suppose we wrote our code on Tuesday and we wrote our test cases on Wednesday, and somebody's changed the code again on Thursday. We want a way of rerunning only those test cases necessary, the test cases that have been affected by the header files or the specification files or the source files that have been changed. Perhaps we began our testing using a native compiler, and then we want to migrate our test environments and our test cases to run first on the simulator and then on the live target, and perhaps verify that as we did that the results didn't change. We might want to associate our test cases with version 1 of the code and then attach them to version 2 of the code and see what has broken as we've moved forward. We might want to take our test environments and split the execution of those test cases across multiple machines, perhaps the machines where the target is connected, and then bring the results all back together so that we have a single report to give to the manager, so that he can get some idea of the progress of the test campaign. This slide shows us a presentation of a high-level coverage view for a system test environment. The source files have been instrumented. You can see that this is a mixed language project, and the system test has been executed. Results have been collected. And we get a very high-level view of the percentage of statement, branch or decision, and MCDC pair coverage that has been obtained. This slide shows what it might look like when we build a unit test environment and we run one or more unit test cases. And we import in the coverage we got from our previous system or functional tests, and then actually focus down on individual executable statements. We want to know whether statements were executed, whether functions were called, whether decision points have been taken for true and false, and right down to the level of MCDC pairs, whether a pair condition has been satisfied or not. And the coverage view shows those things and associates the coverage elements with the test cases that provided them. And this slide shows us what storing our unit test cases in a continuous integration tool might look like. Again, we get a high-level overview of the amount of coverage that's been achieved, whether environments have been successfully built, whether test cases have been successfully executed, and perhaps there are some failing test cases. And as we continue to part 2, the live demonstration, then a screenshot of the photograph of the board that the presentation was performed on. And then just to conclude, various ways in which you can contact Vector Software to ask for more information. Thank you. This is a presentation of VectorCAST working with the Ada-Core GNAP compiler for ARM Cortex-M3. We will show how to use VectorCAST to instrument source code to obtain coverage from functional system testing, and then how to build unit tests to verify functional correctness and increase our test coverage up to the 100% mark. And then finally, how we can take advantage of our test cases over the application lifecycle. Since we're working with the Ada-Core compiler, then our starting point will always be a GNAT project, and in this case it's controlled by a GPR file. And today we have a project which is made out of mixed language Ada and C code, so database.c is a low-level driver type file. So to work with that in VectorCAST, we will begin by creating a VectorCAST cover project. So that asks for a name, call it cover mixed. You can see that we can add in both C and Ada files. We can point to the location where the files are. So we want those 3 files that make up the compilable linkable project. And then there are various footprint type options. And just today we're going to ask VectorCAST to put the instrumented code in the VectorCAST cover environment directory. So now we build the environment, and VectorCAST now allows us to instrument our unit or units for the coverage type, and statement plus MCDC will be appropriate for generally the highest levels of safety criticality. We then step out of VectorCAST and we step into our GNAT tool, most probably, and in this case then I will compile and link and run the test case by using the GNAT command line tools. So there's the compilation, and now it is the flashing. So the GNAT tools obviously use a GDB client, so that needs to talk to a GDB server, that's OpenOCD, which in turn needs to talk to the JTAG controller, so that's an ST-Link JTAG controller for the board. And you can see that after flashing we've executed the test case, and then the results have been collected to memory, and then a memory dump has brought them to standard out. So we can add our results back into our VectorCAST project, and we'll call them cover results number 1. And then we can use the VectorCAST coverage viewer. We can see here that what our system test actually consisted of. Well, the code would normally write to standard out and then read from the keyboard. We haven't got one of those on our target, so we've replaced that with a little while loop there. And so we've placed an order in the restaurant, we've got the check total, and then we've made sure that we added it included dessert. So if we look at the coverage results for this, well, you can see that green, we went there. Red, we haven't gone there yet. Black is not executable code. And then the yellow or the orange are places where we have been, but we haven't been enough yet. So we need to take this this decision point for the true to get 100% decision coverage, and we need to work our way up to 100% MCDC coverage by calling the function under test, so that the subconditions take the right values to build up the pairs. So once we've completed our functional or our system tests, we can close our environment, and then we can build a unit test environment. So we'll choose our compiler profile there. We will choose our names, so UUT and manager and mixed. We will choose a coverage type, which will be the same coverage type as we used in our VectorCAST cover project. We will point to the GNAT project file, which will be, how VectorCAST is able to identify the units that we can add into the environment. So we'll test manager.adb, and you can see different options here for what VectorCAST will do with the missing dependencies. So in our case, manager.adb depends on database.c, and we'll choose to stub all, and that means that VectorCAST will use the hash pragmas that describe database.c to build stubs for the missing dependent functions. So that will all happen automatically as I press the build button. You can see the log there in the bottom left-hand corner. VectorCAST will identify the callable functions we can build test cases for, and it will wrap those with a test harness and a main function. And then the main function will take our test case input values, it will call the function under test, it will collect the expected results and write them back to VectorCAST for the expected values analysis. Did the test cases pass or fail? So it could be that we have some requirements that have come from some external database, and so in here you can see that it's a requirement, steak should cost 14, and if we eat a certain meal we'll get a free pie. So we can prove both those requirements with a test case on place order. So we can, VectorCAST shows us the 3 parameters for place order. So with the first one, well, if we want to sit at table 1, it's as easy as that. For a seat, well, we can choose to sit at a range of seats, means we'll call our function several times. If that's insufficiently flexible, well, we can sit at a list of seats, maybe 5 times. We can sit at seat 2, and so on. Or we can use any legal Ada language code, for example, to initialize a seat with a value which is only known at runtime. Maybe our function call will be in a sequence of function calls. We call that a compound test. And the input to test case number 2 will be the output from test case number 1. What we're going to do today is sit at seat 1. Then wherever there's a composite or a constructed type, then VectorCAST can open it out for us, and where there's an enumeration we can see the values, so we know that we should eat this meal profile here. We should obviously not have a free pie to start off with, so we can see the difference when we get it. We can promote our requirements in there, and then we can just hover over the requirements to remind ourselves what the requirements were. And then at every point where the program counter goes out of the function under test, its place order, into a stub, and you can see here that 2 stubs will be called, well, those become test points for our test case. And so what we can do is we can say that when we call getTableRecord, well, we have control over the object which is returned from the stub. So we can decide that in our restaurant here there's a £5 parking charge. And then whenever we call a stub, VectorCAST can set expected values to check that the values with which that stubbed function is called, therefore their output values from the function under test, well, they must be correct. So in this case we should expect to pay 14, the difference 5 and 14 is 19, and we can inspect an element of an array, so we can say that we expect a free pie. So now when we've got that test case, well, it must pass or fail, and as I press the execute there, VectorCAST is linking the test case executable. It's downloading it onto the target. I can see the little LED flashing red and green, showing that the flashing is occurring. And then the test case execution will follow. The results will be collected by a memory dump by GDB. So here is the coverage that we've collected from our test case. You can see that we ate steak. You can see that we did get the free pie. We can join in the coverage that we got from our that. Our system test VectorCAST cover project. And now our coverage report can show us the combined effects of the system testing and the unit testing. And our objective obviously is to get up to here to the 100% of the coverage types that we need. On the way we can get reports of the test case executions that we've made. So you can see that in here we have got a complete execution report for that test case. As well as test cases that will be designed by the engineer, we have two kinds of test cases that VectorCAST can build for us automatically. We have basis path test cases, which are generated by inspection of the source code and should result in test cases that give 100% statement and decision branch coverage. But of course, they're not going to be connected to your requirements in your requirements package unless you do further work on those test cases. And then we have test cases which can call our function with all the parameters set to boundary values, and that might help expose some kind of failure where the developer did not anticipate edge condition parameters. And then we have a category of test cases here which are built from golden data, external test vectors, conceptually presented in a spreadsheet or a CSV file, where the columns in the spreadsheet match the parameters that VectorCAST can see in the environment. Generally, we complete our unit test by building a regression script, which is a set of files that are perfect for saving away in your version control tool. And the idea then is that by running the regression batch file, it should be possible to rebuild our test environment, rerun all the test cases, and collect off an execution report, and do that entirely in batch mode from the command line. So maybe you do that every weekend. I want to switch away from that environment to so we're going to an environment that we built, the same compiler, but this time the execute method is an ARM simulator. So exactly the same test case, and when I execute it like so, you see the ARM simulator pop up there for maybe a quarter of a second and then disappear again. So we can see the advantage there that we might build our test cases on the ARM simulator, and only when we're confident that they are improving the results we expect that we can move away to the ARM target. So we now want to step away from the unit test tool and go and look at VectorCAST Manage. And VectorCAST Manage can help us with a number of different application lifecycle management issues. So here are the environments that we built earlier, and we've put inside our Manage project. VectorCAST Manage can help us with, for example, identifying the environments that we've built, executed test cases for, but now somebody's changed a header file, a specification file, and so we should rebuild those environments and rerun those test cases. So that's the environments with source code changes. VectorCAST Manage can help us by aggregating coverage that's come from different unit test and cover environments, so that we can see a coverage report which is file-centric rather than environment-centric. It can help us with a summary report on how our test cases are passing and failing. So that's an advantage for the manager as he comes in on a Monday morning after the regression suite has been run over the weekend. Manage can allow us to do build, execute operations at different points in the hierarchy tree, and so that's obviously easier than building batch files that run more batch files in loops. Manage can help us. We can split our project over multiple CPUs and execute different parts of the project on those different CPUs, maybe with different targets attached to them, and then aggregate the results. It can help us add new nodes to our project, and then, for example, we can drag our environments from node to node, and that could allow us, for example, now to execute our environment. In this case, it will be on a native Windows GNAT compiler. Or it could allow us to take the environment that's been built on the simulator and then attach it to a different configuration in which we would execute on the target, and all the while keeping just one copy of the environment configuration in there, one copy of the test case configuration in there, to make ongoing maintenance of test cases much simpler. I can operate my environments from inside Manage, of course, so I might want to, in this case, test scripting, import a test script. So that's one of the regression script file sets. And so here are some tests that we built earlier. We can execute those tests like so. So the simulator will be executed 3 times now. I think one of the test cases might fail. The third one should pass. And so now VectorCAST Manage will detect changes to the configuration. Do we want to accept those changes back into the database? Yes, we do. Do we want to store the results? Yes, we do. Do we want to look at the reporting? Well, here is our report. Manager can easily see red. There's something to identify there. Test case has failed. And then we can go and look, for example, at the, where's the graph gone? There it is. The progress of our test environment. So in this case, the coverage has gone up, the statement coverage went up, the branch to coverage, the decision, the MCDC pairs coverage went from nothing to 10%. But at the same time, the execution results have gone down because at least one test case is now failing. So that concludes our presentation of VectorCAST working with the Ada Core GNAT compiler for ARM.